Hello again and welcome. In this video we're going to be looking at a new meter. This is sold by a company called METERK, I guess. METERK. It's a model number MK01A. I bought this a couple of weeks ago. Actually, I had seen this thing on Amazon. It's probably been about a month and a half ago. And I told my wife I might buy it, and then I went back to look for it and I could never find it again. The whole reason I wanted to run it is I saw what appeared to be a big, huge HRC fuse inside of this thing, and I thought, you know, that fuse probably cost more than the meter was worth. I don't know who actually makes this meter. Maybe the circuit board is marked. We'll see when we take it apart. It just comes with some basic probes. Yep, so there's your thermocouple. Somebody had asked me about the length of these. It looks like 3 feet 7 inches. I mean, to me that's plenty long. You know, the one thing I'm not seeing is the end caps. Alright, so 1000 volts, Cat 3, 10 amp rated. The wire itself is not marked on these. Seems to turn on just fine. Let's go ahead and we'll do a basic functional test on it. Alright, let's just start with AC volts. This should read 0. Should read 2.5. It does appear to be an RMS meter. This should read 2.5 as well. And this should be 2.5. Let's try frequency. This should be 30 hertz. This should be 60 hertz. And this should also be 60. So there's the first problem, is the meter requires a zero cross in order to read frequency. So this is AC coupled through a capacitor. And this is DC coupled, so the output is actually swinging between 0 and 5 volts. Let's just try duty cycles, so this should be 50%. And this will probably go back to 0. Yep. Let's try it at a little higher voltage, so this should be roughly 70 volts. What? Well, that's pretty crazy. Wow. I'm not sure what's going on there. Let's just try it again. Look at it. So this time it's reading 4 volts. And this time it's reading 4 volts. This time it's reading 42 volts. And that's not correct. Let's just bring out the old Bryman here. And there you go. So 67.8 volts. That would be correct. It does not appear to be reliable as far as picking up the voltage. That's pretty bad. Okay, let's try it on DC volts. This should be 5. Looks to be running a little high. Again, we can put this on the standard later on, but you can see with the Bryman. .9994, so it looks like. I would trust the Bryman over this meter. This should read 0. Again, that's a AC coupled square wave. And this should read 2.5. And this should read 2.5 and 2.5. So that all seems fine. We'll try AC millivolts. This should be roughly 115. That looks fine. I believe that's really what it is 118. For temperature, this should be roughly 500 degrees Celsius. And this should be roughly room temp and a little over 1,000 degrees. It looks fine. And then the DC millivolt range, this should be roughly 20. That looks fine. Alright, let's try resistance. This is with a short. It's a little slow on the auto range. Here it is with an open. Again with a short. And an open. Not the fastest meter I've seen. Let's see how accurate it is. Let's go ahead and we'll zero this out. This is a 0.5 ohm. This is a 1% part. Looks like it drifts in pretty good. Takes it a little bit. Let's just try it again. See, eventually it gets there. This is a 1 ohm 1%. There you go. See if it keeps drifting down. Oh, I'd say it's there. This is a 50 ohm. This is 0.1%. Looks fine. This is 100 ohm. Looks good. This will be a 1K ohm. And that's a 0.1%. This is 10K ohms. This is 100K. This with a 1 meg. This is a 10 meg ohm, 0.1%. Looks like it's reading a little high. Let's see if it'll drift down. Oh, I'm saying that's it, so definitely reads a little high. Let's try some bigger values. So this will be a 40 meg ohm. Looks good. Let's try 100. Nope. Now let's try capacitance mode. And so this is with the two leads open. This will be a 150 picofarad. It's too bad it doesn't read a little higher. Then we could zero it out. So one way we could get around this is we could shunt this with an additional capacitor. So this is 100 picofarads. Let's just put this in series. Now it's reading something. We'll go ahead and attach our leads. And now let's zero this thing out. And let's see what we get now. So this is again 150 picofarads. There you go. Pretty much dead on. This will be a 1 nanofarad. Looks good. And a 0.1 microfarad. Looks real good. This is a 1 microfarad. In fact, we can hook this up direct now. Looks good. It's fast, fairly fast. Let's try 10 microfarads. And this will be 100 microfarads. Looks like the larger the capacitor, it definitely slows it down. Let's have a look at the continuity test. See, it's a latching type. Seems fairly quick. Of course, that's not the way we test the meters here. So I can tell you that the open circuit voltage is 1.009. The short circuit current is 419 microamps. If I apply a 50% duty cycle waveform to this, I can go as high as 4 Hertz before the meter will start to miss. The minimum pulse width that it can detect reliably is about 6.67 milliseconds. The resistance that it detects in open circuit is 47 ohms, and the resistance that it detects a short is 46, so it only has 1 ohm of hysteresis. Let's try diode check. So again, this is with an open. Here's with a short. This is with a single diode, and here is 2 diodes in series. Let's try it with a white LED, and you can see it lights that up just fine. And that's roughly 2.5 and 2.6 volts it looks like. Alright, let's try frequency mode, and we'll see if this works any better. I suspect it's going to. So this will be, again, AC coupled. And this is DC coupled. This is at 30 Hertz. Here's 15. And this is 120. Look at this. Our battery is already dying. Oh. It only seems to be affected by... So I'm inputting right now. This is somewhere up in the kilohertz-ish range. Let's just check it again with the Bryman. And you can see it's roughly 3.05 kilohertz. I suspect that this meter is susceptible to that. It's not really that it has a low battery. Oh, you see now it's not, there it is. Isn't that crazy? Yeah, I think that the meter is susceptible to that 3 kilohertz. That's not good. Not very impressive. So let's just try amps. So we'll start out in the microamp range. This will be 100 microamps. Looks good. This is 10 microamps. This is 1 microamp. Alright, so let's try it out with the bench power supply in the milliamp ranges. So I've just got the 2 meters in series. So you can see fairly close. This is 38.5 milliamps. Let's just try turning it up a little bit. You see this thing's fused at 600 milliamps. We'll go up a little bit further. Update rate on the Bryman slow because I've got the AC being displayed. Yeah, you can see both meters correlate fairly well. Let's switch it over to amps. Again, both meters reading roughly the same. The only other thing we need to try out is the non-contact voltage. See, I've just got a cord. Let's try to turn this thing on. Yeah, let's see what happens here. That seems to work well. Alright, see, it has a manual range function. Obviously the 0, the hold is just going to be a hold. You can try a min max. Yep, that seems to work. And you can see you can cycle through them. So functional wise it looks pretty good. Alright, so one of the things somebody asked was how stable is the meter on the stand? You know, I don't know, what's your criteria for it? I guess one of the concerns was with this little tiny meter. I only have this one left. So I guess the thought is that this meter is not stable. You know, really, to be honest, the problem I normally have with these is you put some leads on here and this is what happens. So I'm hooking this thing up to stuff and then the meter falls over, and it's not really that the stand is too narrow, there's just not enough weight. You know, this meter is quite a bit heavier. See, I could drag this thing pretty much all over the place and there's no problems at all. Of course, the same thing with the Bryman. This thing weighs a lot, and you can see this doesn't budge at all. Still my favorite meter by far out of any of them that I've looked at. I keep thinking one day somebody's going to make a meter that I like better than that, but it just hasn't happened yet. So this meter will actually make a fairly good oscillator. So what you want to do is put the tilt somewhere about this angle here, and all I'm going to do now is set this thing in motion. See if we can get it started. There it is. Can you hear it? Hear it running? Got to reset our bail. Runs for quite a while. So I have both these meters connected in parallel and they're attached to my Fluke reference standard. I just turned that standard on. That thing has to be turned on for at least a half an hour before you're going to get any kind of accurate results out of that. So I'm assuming that it'll start to drift down. But you can see this meter is definitely reading a little bit high. And this is with 1 volt being applied. Let's just try it in the millivolts. Yep, that overranges. And this is with 1 millivolt being applied. It's on my left. You can see I have one of the high voltage power supplies out. The output of this is attached to our 2 meters. Let's go ahead and turn them on. And we can apply a little bit higher voltages. Let's just see. So there's roughly 49 volts. Looks like it's reading a little bit high. It's 95.8. Again, a little high. 161.7. Again, a little high. Now they claim this thing, yeah, is Cat 4 600 volts. I assume then this is a 1000 volt, yep, 1000 volts DC. So let's go ahead and take this thing on up higher. So here's the maximum of our power supply, so 982. So definitely it reads a little high. What we'll do is just invert the polarity, so 227.9 and 228, so that appears fine. I've seen meters where they'll have like a big offset between the two polarities. So I've reconfigured this power supply to put out an AC voltage. You can see we're putting out 542 volts AC. The DC offset is 1.6 volts or so. What I'll do now is just vary the DC offset. Let's see how that affects this meter. So there's about 240 volts of offset. Let's try going up a little higher. There's 300 volts offset. Let's try going negative with it. Again, that's 300 volts negative. It doesn't appear to affect the meter, so that's pretty good. I've seen meters again where you introduce a DC bias and it really screws with the meter. So this one does not have that problem. Let's just put this into DC mode. And that's kind of interesting. You can see it does not pick up the DC offset. So if you wanted to calculate the AC plus DC value with this, you can't do that with this meter. I would expect this meter to right now be displaying that 277 volts. Let's just try it with a positive voltage. Yep. Same thing. I mean, that's 300 volts of DC offset, and this thing's basically reading 1.5 volts. It's not correct. Alright, let's try changing the frequency. So again, and you can see we're currently at 50 Hertz. Let's just try going down in frequency and see if that has any problems. When it's all the way down to 10 Hertz, you can see it's still reading just fine. It's all the way up to 400 Hertz, it looks fine. So again, both meters are connected in parallel to my function generator, and I'm currently outputting a 1 volt sine wave. What I'm going to do now is just increase the frequency, and you'll be able to follow that with the Bryman. And let's just see what the 3 dB point for this meter is. So it looks like just a little over 3 kilohertz. That's pretty much what I would expect for a meter in this class. So this is an interesting problem. So I'm currently sweeping the frequency to see if there were any areas that this meter was sensitive. So I'm outputting 20 dBm right now. So that's roughly 3 volts. So this is currently at 184 megahertz. And you can see the meter is reading roughly 56 volts. And again, there's only 3 volts being applied. You can see as I put my hand around it, there's 28, 15. Let's just try turning it on. That comes right back into it. Let's see if there's any other spots where it's sensitive. So I tried going from the COM to both current inputs, and I did a full sweep up to a gig. It looks like in the milliamp setting, again, that 180-ish megahertz affects the current input, but that's really the only thing I saw. The DC voltage mode does not appear to be susceptible. So let's put it back to the frequency mode. Wow. So 661 kilohertz right now. What I'm going to do is just go ahead and take the frequency on up, and let's see where this thing tops out at. This is 57 megahertz. There's 70, 80. Oh, right there. Let's try turning up the amplitude. So this is with a little over a 3 volt signal right now, and you can see where we can read all the way up to 102 megahertz. So pretty impressive. I've seen that with some other low cost meters, including I think that Casun test. I think that one we read all the way up to a couple hundred megahertz. So let's have a look inside of this. I do like the names that they come up with for some of these batteries. That's a nice tight fit. It's probably the tightest fitting boot I've seen. Battery fits nice and tight. You can see it is marked for the polarity. I don't know if we can put this in backwards or not. Let's just try it. Oh yeah, it's very easy to put this in backwards. You know, and I doubt, yeah, I can't tell a difference. I doubt very much that they have any kind of protection for reverse battery. You know, there's not a lot of markings on the circuit board. It says VC17B 890 AVO.7 2016, so it's a fairly old meter. But I don't see any other markings that would indicate who actually makes the meter. Looks like 600 milliamps, 250 volts. This is marked Ref 1 10 meg. And then it has Ref 2 10 meg. It looks like Ref 1 is just jumpered out with a solder blob. You can see the shunt here is hand soldered. Actually, all these connectors are. There's another jumper up here that it looks like they removed. Looks like ACMO. I'm not sure what that would be. My guess is this looks about the same as the others. You can see right here's our PTC, and here's our two transistors back to back. That's forming your clamp. This is your ground plane here. So virtually no protection, I'm assuming. 380 volts, 100 kiloamps. Now you notice that there is no DC rating on this at all. And what did they say this was? Cat 4 600 volts. Sometimes I think it'd be nice to be able to supply something like, you know, 20 to 50 kA to some of these fuses and just see what happens. You know, I would not be surprised if this wouldn't come apart. Another member at the EEV blog site had actually broke this one open. Of course, it was not filled. You know, kind of common that you see these cheap ceramic fuses with no sand. I seriously doubt if there's anything at all on the back side of this. I expect it to be just like the Iec meters. So again, first thing I notice, what do, they sink the via right smack in the center of each one of these pads. And I've seen that before, where what ends up happening is the contacts, as you switch this back and forth, erodes where that via is, and eventually you end up with this big wear hole in the middle of the pad. What I don't see with the meter though is a lot of copper. That's a good thing. The other thing I notice is it looks like maybe this pad here from this outside contact, and maybe this pad here, and up here are the only three that are exposed. So again, what you don't want to have happen is you rotate this switch, it actually cuts through the solder mask, and eventually it'll just short out these traces. And you can see this is all flux residue from when it was soldered. You know, but all in all, it just basically to me looks like a larger version of that Sun test meter that I tested. You know, you have the non-contact voltage detection and all the other features here, so that's kind of nice that, you know, at least you don't have to add buttons to it. Again, this is our input trace right here. You can see it's pretty close to this fuse. You know, could I get this thing to arc? I'll bet you I probably could. And so we can see there's a via right here that punches through to here, and then all four of these resistors are in series, so that's making up your high voltage network, if you want to call it that. And then this other one that goes off to this main trace, this is going to switch in this PTC and clamp depending on what mode you're in. Nice thing about this meter is because the current is not shared with the voltage input, so this fuse isn't engaged all the time. That's one of the things I don't like about the Iec meter. And as a matter of fact, when I had modified that meter, that's one of the things I did is I broke that trace, so I ended up making it, I think, a microamp meter, and I changed some of the shunt values, and I ended up putting a larger fuse in there, and then it doesn't have a 10 amp fuse any longer. It almost looks like a nickel plate. Might be interesting to do some kind of a switch test on it. Got a nice click to it. Alright, so I was putting the meter back together. You notice something missing? Like right here? Look at this. See that? The solder never even wicked to this. See, I just slid right back in there. This just fell right out. Probably don't want to be putting 10 amps through it with that not being soldered. So let's just go ahead and correct that real quick. So I'm just going to mix some leaded with some lead free, because I just don't care. And the rest of them look fine. I think that's the only problem. Alright. No worse for the wear. It's probably a little better now that we've corrected that solder problem. Alright, time for a drop test. Again, this is going to be about 1 meter up. Again, this is onto a 2-inch thick piece of hardwood that's sitting on top of the concrete floor. Alright, so this is what's happened after I've drop tested it. Notice that the large fuse is not captivated. Normally, like the smaller fuse here, see how they have these retainers on the ends? The large fuse holders are not made like that. And the case does not have a retainer built into it as well. So that's no good. It's like, use better fuse holders or change your case design, I guess. That's kind of a no-brainer. I'm surprised that they would miss that. Alright, we're back out in the motorcycle trailer. So this is some VP C16 gasoline. This is a racing fuel. I'm going to apply that to the lens and lettering of the meters. So this is the new Harbor Freight meter. Looks like they managed to make these a little cheaper. Look at that. No effect at all. You can see what this has done to this cheap Iec meter though. I rub this on here. Immediately it attacks it. I don't know why they make these meters so cheap. Alright, let's try the new meter. Yeah, no problems at all. It's good. Yep, it's not sticky or anything. Okay. As well as this, so that's a go for the METERK as well as the new Harbor Freight meter. Of course, a bad deal for the Iec. You can see how that thing's drying up. It's actually sticky right now. People ask why I test this. Well, if I have a meter, which I actually keep one out in the trailer with me, and it gets splashed at all with any kind of fluids, I don't want it to screw up the lens of the meter. I mean, it's literally ruined this meter. Look at how bad that is. If this meter still worked, I don't know if you could still read the display. So during my last video, I had asked viewers to go ahead and leave a comment if they'd like to see me try to modify this meter to survive these transients, because I know that this thing is going to fail at a fairly low level, or just run it like I do every other meter. And you know, there's some split. Some people would like to see it, you know, go through some basic tests and hopefully I can repair it and then I can try to modify it. Chances of being able to repair this meter after it's damaged, slim to none. It's a very small percentage of meters that I'm actually able to repair. It really comes down to the quality of the meter, to be honest. Some of the meters, like these Brahmins that I've damaged, it's basically just taken out a few transistors. Same thing with all the fluke meters I've damaged. It's typically just taken out the high-speed clamp, and you know, it's a fairly quick repair. This thing, when it goes, it's probably going to take out the main IC chip, and that's going to be it. So that option is out. As far as making modifications to this meter, the UT181A was, I think, the first one that I modified. That meter was damaged with nothing more than a single zap off of a small piezo grill starter. You know, it was pretty dramatic. You know, it's like a $300 meter, and you'd expect it to survive that, but, you know, one hit. And when I started looking at the circuit board on that, that meter's got some layout problems. But it had all the components there to protect it, so basically I changed the circuit board layout a little bit, and that meter survived quite well. Another one that I modified was the UT61 by Unity. Again, that meter was damaged by ESD. I damaged quite a few Unities that way, and so I bought a brand new meter just to modify it, and I went through a complete analysis of why the meter fails and what it would take to improve it. There were quite a few posts on the internet. People were saying, oh, just put these MOVs in there, and that's going to really improve the robustness of that meter. And, that's just basically false. The MOVs aren't going to save it at all from the ESD, and I showed that during that video. So the last meter that I modified was this little Casun test. And of course, if you go back and look at the video on this, this thing has been butchered. It's just packed full of parts up in this area. But this thing now is probably bulletproof. The switch won't survive. If I put this on my switch cycle tester, this would fail pretty early on, but at least as far as the front end's concerned, this meter is now pretty tough. It survived a 14,000 volt hit, and it's still functional today. I don't have a problem, I guess, with modifying meters, except in the case of meters like this. So let's just go over what some of the problems are with this meter. First of all, the 10 amp current shunt was not soldered. I can fix that. And is that a reason not to modify the meter? I wouldn't say so, not in of itself. The next thing is they put the vias in the pad of the rotary switch. Again, not a good design practice. I've seen that with other meters. This Casun test is like that. Another problem with the meter is I can flip the 9-volt battery. There's nothing in there that prevents you from doing it. As a matter of fact, if you look at the UT61E, it's very similar to this meter, but they have a different gap for the plus and the minus. So essentially it prevents you, and lets you really force it, of putting the battery in the wrong direction. Now, I've heard of people putting in those batteries backwards, but you'd have to be trying. On this meter, it's pretty easy to do that. So you better pay attention. Of course, this meter, when it's in the AC mode, requires a zero crossing to read the frequency. Again, I've seen that on other meters. It's not a major problem by itself, but, why? The meter is very slow to auto range, especially when you're looking at low resistance values and high capacitance values. I could change out the large fuses fuse holders to help captivate that fuse if you drop the meter, so that's fixable. And of course, the meter is susceptible to 180 some odd megahertz in the AC mode. The fact that this thing reads like almost 60 volts when there's only 3 volts applied, that's just crazy. And the fact that when you're putting a 3 kilohertz waveform into it, and it's basically showing 4 volts intermittently, I can almost forgive the 42 volts, when it does show a voltage, because, this meter doesn't really have a very high bandwidth. But the fact that it reads 4 volts a lot of the times, that's just crazy. Another thing that I just don't like about this meter is that if you have an AC signal and it's biased at all with a DC voltage, you can't pick up the DC bias with this thing. You switch this meter over to DC, it should read the DC offset, and it reads nothing. Even with like 300 volts applied of DC offset, the meter reads nothing. So I think that the meter just has so much stuff going against it, I'm not going to waste my time trying to rev it. So for those of you who wanted to see it, go back and look at my Unity UT61E meter that I've modified, or this Casun test meter. Those videos will give you a very good idea what's involved in making these modifications. It's not trivial. It's not something that's going to take me 5 minutes or something to do. It's probably going to take me a day of work by the time I put the changes in there and actually prove that those changes were effective. And to really what end? The meter's still going to be a piece of shit. So I think I'm just going to run it. So let me go ahead and get this thing set up. Okay, so I'm going to start my testing with looking at the fuse inputs. I saw a couple of interesting posts recently. One was talking about basically the fuses are not there for safety. They make these fuses with these break currents exactly for safety. Again, if you look at the Iec Standards, this is on page 28 of 61010-2-033. So there are several 61010 standards. This is the one specific for handheld meters. So these are the CAT ratings here, and you can see for a category 2, short circuit currents typical in Ka less than 10. For a Cat 3, less than 50 Ka. For a Cat 4, greater than 50 Ka. Short circuit currents are calculated for 1000 volt line to neutral voltage. So when you're wondering why they put a 1000 volt 10 Ka fuse inside of one of these meters that's been certified, this is why. Alright, so you can see I have one of my high voltage power supplies out. The output of this is attached to our attenuator, which goes back to the Brahmin on the left. This is divide by 10, so 1000 volts on this would equal 100 volts on the Brahmin. I'm going to be applying 2000 volts to these current inputs. Somebody had said that, you know, in all the manuals they say that, you know, you're not supposed to exceed a certain voltage on these. So again, this is out of the same standard, and I've been over this before, but you can see if the current protection device is a fuse, it's replaced with an open circuited fuse. And then what are we doing? We're applying a voltage of 2 times the highest rated voltage for any terminal. It's applied to the terminals of the overcurrent protected measuring circuit for a minute. The source of the test voltage will be capable of delivering 500 VA. During and after the test, no damage to the equipment shall occur. So again, what I've done in the past is I've run these without a blown fuse. The idea of having the fuse in there is this could be sitting, especially on a meter like this could be cocked all over the place, and that could actually change the distance from this to, you know, a return path and possibly cause it to break down at a lower voltage. This is the fuse that you saw me blow in a recent video. Of course, this power supply is not rated for 500 VA, but at least it'll give us an idea if it breaks down. Just in case, again, that you're not quite following, this meter right there is marked 1000 volts DC max. So we're going to be applying 2000 volts. Let's just change this over to DC, speed up the meter. There's 800, there's 1000, 1500. There you go, just slightly over 2000 volts. Alright, so they want it applied for 1 minute. So let's go ahead and turn it back up. There you go, 1000 volts, and we'll just let it set. Alright, and let's do the same test on the low current input. Unfortunately, I don't have a fuse blown on hand, but again, let's go ahead and take it back up to 2000 volts. Looks good, and we'll let it set a minute. And there you go. So no problems with that test at all. So the next test we're going to perform is this transient generator will apply a full rectified 220 volt signal, and we'll apply that right to the voltage inputs of the meter, and then we're going to switch the meter through all of its different functions with that enabled. And again, this transient generator will limit the amount of current that it puts out, and that's programmable, so even if something goes wrong, this thing should try to save the meter. So let's go ahead and turn on that output. And if we're in the AC mode, really, it's showing nothing. Do I believe that? Probably not. Let's see what the Brahmin shows. This meter, I'll tell you, this is part of the reason I won't modify it. So there you have it. That's what it should be reading, about 110. You can see it's 111 volts. It appears that the meter just can't pick this up. So let's try it in the DC volt mode. Does it read that? It does. Let's see what the Brahmin reads. So fairly close. So it appears not to be just a case where the meter can't read an AC voltage with a DC offset. It cannot read the AC voltage when it's been fully rectified. This meter's just full of surprises. Alright, let's try the... Oh, see the battery light came on for a second? And again, we won't run it through the current inputs. Alright, so let me go ahead and functional test it. The meter passes functional just fine. So the next thing we're going to do is take my piezo grill starter, or piezo as I call it. Again, I've documented what the output waveform of this looks like. That's in a couple of different videos. Feel free to go back and look at those. This test has damaged a lot of Unity meters, including a very high-end Unity UT181A. One hit with this is all it took, and it took that meter out. Alright, so this is going to be 5 transients with each mode of the meter, except the current and the non-contact. And then I'm going to flip the polarity around and we'll repeat the process, and then we'll functional test it. It's funny how it resets. Oh. Unbelievable. I was running this test for the fun of it. Totally dead. That was supposed to be a do-nothing test. I brought up the gun and I was planning on running it through this. Yeah, I never figured this meter would have failed this way. Again, I ran AN860, which is very similar to this meter, and it survived this test just fine. As a matter of fact, it survived that, and I believe that meter got damaged at 4 kV. I also ran the ZT102, which is the one that you saw where I had modified, that's got the Grim Reaper on the back. Originally, the first meter I tested failed at 3 kV, but it survived all this ESD testing, and it certainly survived this. And I also ran that Iec 8008 that the lens is all etched up on, and again, that meter survived that test just fine. It didn't get damaged until a 2,500 volt transient off of this generator. I never would have expected this meter would fail this way. There's nothing I can do to repair this. Unbelievable. That's a test that I thought only Unity meters fail. Alright. Next thing I'd like to do, now that the meter's damaged, is go ahead and dissect these fuses. But before we do that, I want to pop them. So these leads in the meter are supposed to be rated for 10 amps. See how that molding, I mean, you can get that in there, but it's just a terrible fit. Alright, so off to my left, you can see I've got the big power supply out. Alright, so we'll be starting at 500 milliamps. I'll increment it by a half an amp every 30 seconds until the fuse opens up or something else fails. Looks like it's dissipating 8 watts right now. These are a little warm. Fuse is fairly cold. Shunt's starting to get pretty warm though. It's dissipating about 15 watts now. Yeah, the shunt's really getting warm. The fuse is starting to get fairly warm. See how the shunt is starting to discolor? The whole system is now dissipating about 65 watts. We're putting about 15.8 amps through the whole system. The leads are starting to get very pliable. We're now dissipating about 100 watts. There, the fuse finally blew at 18.3 amps. Oh, really? Looks like something else. I wonder if the leads failed. Let's check our red one. No, that's fine. Let's look at our black one. Yeah, it looks like our black one went. Wow. So we damaged the lead before we took out the fuse. Alright, so I have my own leads attached to it. This is a little bit better wire, I'm sure. This time I'm just going to start off at an amp and we'll sweep by increments of an amp. Also decreased our dwell time to 15 seconds. In case you don't remember the plots, the far left LCD is showing the resistance, the center is showing the current, and the right one is showing the power dissipation. So currently we're putting out about 12 amps. It's pretty high. Alright, you can see the large one is popped. If you look at the small one, you can see it's dropping about 0.39 volts. So this is actually hooked to my bench power supply right now, and I'm putting out roughly an amp, and it hasn't popped this fuse yet. Let's go ahead and take it up higher. That's with 2 amps applied. See that thing glowing? Let me turn off the light. Check out that fuse. It's just glowing like crazy. That thing is just cooking. Huh. Wonder how long it'll live like that. I'm going to try going up a little higher. Oh, right there she popped. It's about 2.2 amps, but at 2 amps I think it just would have sat there glowing. I have a hard time believing that this fuse wouldn't pop before the leads did. There's our fuse element, at least part of it. So just a ceramic tube. And it looks like the caps are just pressed on. I think it just basically captivates the wire. Just a press fit. Could actually reload this cartridge. That just broke the ceramic. And sure enough, you can see it's not a filled part. There you can just see the fuse element, but definitely no filling. So this next test is something I saw a YouTuber named Voltlog do. Basically, it hooked up a bunch of pocket meters to an insulation tester, and then he rotated the meter through all the different modes, and of course it loaded down that insulation tester. So instead of getting 1,000 volts across the meter, I think he ended up with like 4 volts or something. I have my big power supply out again, and we'll just set the meter to its ohms mode. That's going to engage this clamp. This power supply is very dangerous. You saw me pop a fuse out of my Bryman last time I used it. Alright, hopefully we can catch this. Well, I think that's going to be it for this video. I hope you enjoyed it. I'm not too impressed with the meter. It sure looks like it has a lot of problems. Well, until the next video, later.